To the VHIN webinar series for September 2024. This is actually the anniversary, I think, of when we started this webinar series. I was just looking back and we had the first one a year ago in September. Today we've got Alex Wang speaking. I'll introduce him shortly. But before I do, and because it's the anniversary, I thought I'd remind people and especially people who aren't quite aware what the Virtual Health Information Network is. So we were set up nearly 10 years ago now. We set ourselves up to facilitate research in the whole population data area, which pretty soon focus on the integrated data infrastructure, although that's not the only thing that we help people with. And it's got health in the name, but we help people with health and social research, I think it's fair to say. The website is there, vhin.co.nz. If you go there, you'll see guides for how to do various things and some snippets of code that will help working with data. And if you join the Facebook group, you can also participate in discussions, so ask people questions. That's been superseded a little bit by ID Commons, which I know a lot of people will be involved with. And also we run courses. So we run 3 now. The first one we set up was Introduction to the Research in the IDI course, which just explains what the IDI is. It's a 1-day course. It's full for this year, but there's the QR code there for it if you want to have a look. And these are, in the next time we run courses in November, December. There's also a 4-day Introduction to SQL course, which is useful for anyone working with microdata of Stats New Zealand, particularly in the IDI. And then there's this new one that we've developed, which will be run for the first time in December, which is hands-on practical skills using the IDI actually in a data lab. So it'll be in the Stats New Zealand Data Lab on the 2nd to the 4th of December. So if you're interested in that one, please click the QR code and it'll take you to the link for the course. You can also go to the website at the bottom to get to all of our courses that we run as part of the New Zealand Social Statistics Network. And these 3 are just 3 of those. There's others as well. Okay, today we've got Dr. Alex Wang, who works for MBIE. He's a data science manager, and he's also a research associate at Te Herenga Waka, Victoria University of Wellington. He's a statistician and data scientist by training, with expertise in data analytics and machine learning, particularly for tabular data. And his research interests include tabular data synthesis and multimodal data-centric AI. He successfully defended his PhD recently, and that aimed to develop efficient algorithms for tabular data synthesis. He's going to talk a little bit about that today. And as part of that as well, he developed a comprehensive framework for evaluating synthetic data, and he may touch on that as well. So I'll pass over to Alex, who's going to talk about data-centric AI, enhancing public research on social data through synthesis.
Cool. Thank you, Barry and Martin, for organizing this for me, and thank you guys for your time. Tinakoto Katua, ko Alex Toko Inwa. My name is Alex. I'm currently working for MB as data science manager and also a research associate with Victoria University. So here is the topic I'm going to present today. So data-centric AI, enhancing public research on social data through data synthesis. And I'll cover this presentation by 5 sections. Without further ado, let's just get it started. Introduction. So I think everybody's talking about AI at this moment. So AI, artificial intelligence, in a high level, is just including 2 components, data and algorithm, basically trying to train algorithm on historical data, make some prediction on that. So far, a lot of efforts and investment has been invested into the algorithm part, where we have our algorithm, especially in the deep learning part, getting wider and deeper, while the focus on the data part is limited. That's the reason why a few famous researchers calling the shift from algorithm to data, and this is where the data-centric AI coming from. All right, I think everyone has been aware of that. We are in an area of digitalization, and thanks to digitalization, we got a huge amount of data created on daily basis, got stored in different systems. So that sounds like a very good news, and it sounds very intuitive. We got data, we can make decisions. Simple like that. Actually not. There are a lot of important constraints when trying to use real data in our daily life. It could be quantity, where we need a lot of data, where the collecting data is very expensive, or it can be quality issue when the data is imbalanced or biased, or there's a privacy issue with real data, then it is only available to certain group. So then the research question here will be, is there any solution we can utilize to address those three data problems? Yes. So basically, we believe, I think synthetic data is a very pivot tool from data-centric AI, which provide a solution to address the data quantity issue through data augmentation. So we can generate more data when we need more. And also, it is also a tool we can use to balancing data, which is addressing the data quality issue. We can generate a specific class of data here if a specific class of data is needed. And finally, we can use that for representing real data when there's a confidentiality issue with real data. Okay, so the overall goal about synthetic data from data-centric AI, as I said, is trying to augment real data when more is needed, balancing specific data when we need it, and addressing privacy concern to represent real data when there's a privacy issue. I'll give some real examples from our daily life or government sector. So from the data augmentation point of view, sometimes we can see the data is very expensive to collect and label. So nowadays, digitalization collection is not a problem, but labeling is still a problem. That's the reason why Google is trying to use us as free labor doing the labeling about, can you please click the traffic light from those pictures? Yeah, so if we use cybersecurity as an example, so we know when the hacker trying to attack a server, then there will be an outlier event got captured in the system, but all of those outlier are real event, right? And it's very hard to label those events manually. So synthetic data can be used to augment those events from data augmentation point of view. And then data balancing or data debiasing from the data quality point of view, I think it's very obvious in health domain. So because for certain disease is common, we have imbalanced distribution of the diagnosis. Only a small amount of patients got diagnosed for a certain disease, while majority doesn't have this problem. So then this biased distribution is problematic, especially from machine learning prediction point of view. So synthetic data can be used to debias or oversampling to restore the balance of the distribution. And from the bias point of view, we know there are certain group of ethnicity is underrepresented represented in a database. Then synthetic data can be used to oversampling that part of samples as an efficient tool. And finally, data representation. We're talking about data privacy, and Stats New Zealand IDI is always the topic we try to talk about within New Zealand, right? The data is a national level data asset, got huge potential value, but because there are certain rules or barrier which limited the research can be done within IDI. So synthetic data in this case can be a useful tool to promote public research on IDI data. I'll cover that in details later on. Background. Okay, so tabular data synthesis. Then the first question is, what is tabular data? So tabular data basics table data. We got columns and rows, where those things we can see on daily life in Excel or in relational database. Tabular data is different with image data, with audio data, because tabular data got heterogeneous data types. You can see date, you can see continuous variable, categorical variables, all kinds of type of data, which introduce the further challenge, and which I'll discuss in detail later on. Then tabular data synthesis. What's synthetic data? Basically, synthetic data is not real, but trying to mimic the statistical distribution of a real data set. In a high level, we can break down the synthetic data approach into three steps, three types. First one is fully synthetic data. Basically, you're trying to generate a completely artificial generated data. nothing to do with real data. And second one is partially synthetic data, where there are sensitive features are in place. I'll give example. For example, if talking about job seeker data, in the real data, you will probably see the company name in one of the variables, and because the company name is commercial sensitive in the variable name, which means we just need to generate synthetic data for the specific column, while the other job title, location, they all generic, and we don't need to worry about it. Then that's the place when we're trying to apply partial synthetic data. And finally, hybrid synthetic data. Basically, we're trying to generate synthetic data on real data, and we mix them together to make a bigger data set. That's a hybrid approach. Okay, so in another name, synthetic data is generated by an algorithm. And in a very high level, this algorithm can be called generative AI. And we can see generative AI application has been emerging in so many different data modality, including famous ChatGPT, image, audio, drug discovery, etc. And they are pretty amazing, the results. So for example, if we look at the image part, way before generative AI is turning into a hype due to ChatGPT, synthetic data has been used a lot in the image side. So for example, this website has been built probably back in 2018 or 19. Whenever you refresh this website, it will generate a realistic image, but those people are, they don't exist in the world. They're just synthetic image data created by the generative adversarial neural network model, which is pretty amazing. Okay, so the question will be, if generative AI has been so successful in text or image, in audio, or in drug discovery, then why do we still need to do research in tabular data? Why do we not just adapt those algorithms into tabular data directly? Because there are a lot of challenges trying to do tabular data synthesis compared with image data, audio data. So the first one is manual data collection. That's the data. That's the fundamental reason of the challenge. Because for image data is captured by a machine like camera, or for audio it's the same, right? If you capture by a machine or equipment, the data structure is always standard. Okay, and there's no special case in that. But for tabular data, it can be collected by so many different ways. And there's inconsistency of the features or length or the structure of the data. The second layer is the heterogeneity, as I was talking about. There are diverse data types. For image data, for example, it's all represented by pixel, right? The pixel value could be from 0 to 256. So it's a certain range in numerical format, so which is make it easier for deep learning model to be applied on. But for tabular data, you got categorical variables. How do you treat the categorical variables? Will have different meaning for the deep learning model, and also the synthetic data quality. So all of those are still open question for deep learning research to be resolved for tabular data. And the third one is task-specific generation. So for image, to be able to generate as realistic as possible or as diverse as possible is the ultimate goal of image synthesis. But for tabular data synthesis, there can be different initiatives we're calling for synthetic data. It could be used for machine learning training, or it could be for simulation. It could be just for training where you need some low fidelity synthetic data. So depending on your underlying or downstream tasks, you need different way of generating synthetic data in different settings. And finally, evaluation challenges. So for image and audio, it's very easy for human beings to evaluate them using sensory ways, right? You can see the image to compare with the real image to see if it's clear enough, real enough. For audio, you can listen to it. But for tabular data, if I give you a real table and a synthetic table, you can't compare it one by one, because the real property of tabular data is in the table structure and the statistical properties instead of the visual or audio way. So those four are the fundamental challenges of tabular data synthesis. Well, But the good news is that there are heavy amount of research has been done in the tabular data synthesis part without realizing this is related to generative AI maybe. So the first model will be a perturbation-based model. Basically, you're trying to ingest some noise in the real data or doing some nonlinear transformation for the real data to create fake data. So the limitation is very obvious here. There's no novelty of the synthetic data, and also it doesn't allow you to augment the real data because it's just trying to apply noise into real data. The second one is manual specification. I think if you got domain knowledge about a specific table, you can create up some role manually, and you can, based on this role, to simulate data. Again, it requires a lot of domain knowledge, and also is time constraint, and it's very costly to set this up as well, and it cannot be scaled up for general use. And the distance-based model. So in machine learning algorithm, there's one specific algorithm called synthetic minority oversampling technique. This technique is used for oversampling minority samples. Basically, you find a real point, you find its neighbors, and you're trying to generate synthetic data between those 2 points in the middle line. And unfortunately, this method is the only method available from machine learning family within IDI. And if you're trying to do IDI, I think SMOT can be a very good starting point to try. And there are some variants about SMOT, including SMOT NC, which is taking into consideration about categorical variables. Basically, we introduce some loss term if the categorical variables are different. And also Chris Ball from Reserve Bank, New Zealand, he developed a distance-based algorithm which can be used to generate prototype based on the average of the group. They all belong to distance-based algorithms, in my understanding. And another problem about distance-based algorithm is the sensitivity about the distance matrix you choose. By default, people choose Euclidean distance, but there are more than 30 distance metrics you can choose. And the different distance metrics will generate different results. And so there will be some tuning process you need to do to select the best distance metrics when we use this algorithm. Regardless of this, the biggest problem of distance-based model is there's no novelty about your synthetic data. Basically, you're trying to use your existing data space to generate the synthetic data, and the synthetic data is all within the existing data domain. So there's no novelty of your real data, which means probably there's no information gain in that case. And from statistical distribution point of view, there are algorithms to be based on distribution with some prior assumptions. So for example, SynthPop, developed by a researcher from University of Edinburgh, is another package you can use within IDI, and it is using classification and regression tree. Basically, for continuous variables, you just do sequential regression. You do regression of your column 2 on column 1, then column 3 on column 1 and 2, column 4 on 1 and 3 and 4, 1 and 2 and 3, etc. The problem here is very obvious. One is it cannot. If your prior assumption is wrong, then the whole fitted distribution is wrong. The second one, again, same as the distance-based model, is it cannot handle large data. So even you have enough computational power, it will take forever to run. And finally, is the distribution-based generation model from learned joint probability. And another fancy name of this is deep generative models. Basically, it's a generative model with deep neural network. Okay, so what is deep generative models? Deep generative models is using neural networks trying to learn the complex joint distribution of the real data. Then once the joint distribution is learned within millions of hyperparameters within the neural network, then basically you can use this learned distribution to simulate synthetic data. So the advantage here is very obvious. So it doesn't have any prior distribution assumption. Basically, it can learn complex data density without prior distribution assumption. And also, you only need to train it once. Once it's trained, then your deep neural network memorize the joint distribution of the real data. Then you can generate as many data as you want without set limitation. In addition to that, if you can tweak the deep learning model with a labeling over there, then you can train the model based on the condition of the label. Then you can do conditional generation. So for example, if you train a deep generative model based on a label of gender, then it can be utilized to generate data for male only or for female only as an example. And also deep generative model giving us the chance or opportunity to explore population synthesis, which will require a lot of data and computational power. All right, I think it's enough about those technical details. Let's step into some real applications we have done during my PhD research and collaboration with many people within New Zealand. The first one is recently we've done a synthetic data project on data governance in the government sector. What we found here is that high data utility is not always necessary, right? I think, yes, it would be ideal if we can generate synthetic data as real as possible. However, at the cost of privacy. But we all know that different downstream tasks will require different levels of fidelity of synthetic data. Realistic synthetic data is not always the end goal. And we propose that different levels of synthetic data can be used in different applications in government sector. So for example, let's start with simulated data. If you got a schema dictionary of your real data set, you can just simulate data from the schema to generate synthetic data. Okay, or we call it dummy data. Basically, it's the variable name is the same as real data, and the data type is the same as real data, but it doesn't contain any detail level information of real data, because as you can see here, you don't even need access to real data to simulate the data. So there's no privacy issue. And those kind of data is very useful for code developing, for training, etc. And then in the middle land, we got something we call low fidelity synthetic data, which will be generated from summary statistics instead of the real data. Again, the privacy risk here is very, very low because this model haven't seen the real data. It's only based on the summary statistics of the real data, which can be seamlessly applied in IDI case. And I'll cover more in the live demo later on. And finally, is high fidelity synthetic data, which will require training the model on top of real data, and also it will require a lot of data evaluation, especially from a privacy point of view. But all of those three levels of synthetic data are useful in government sector and can be applied in different use cases. All right, then move on to the IDEA project. I've been collaborating with researcher in Victoria Uni and Auckland Uni, including Barry as well. So to our best knowledge, this is probably the first or the second most comprehensive investigation within IDI for high fidelity synthetic data. Basically, we started with a very ambitious goal, but then we are forced to narrow down to focus on census data plus a flag created from IID data only, due to many reasons. Then we constructed raw data, and through the raw data, we did a explainable machine learning model trying to identify the key features for data synthesis. Basically, for synthetic data generation, you need to understand which variable you need, and you only synthesize what you need. Don't try to synthesize the whole table while you're not going to use some of those variables. And after that, we try multiple ways to generate synthetic data within IDI, and we'll give it to the release check team. The release check team takes like 4 to 6 months to do the release check, because at that time it's a brand new topic for them. So there are a lot of conversation back and forth, and finally we got the data related. And the overall conclusion from this project is synthetic data is useful in stats using an IDI environment. However, there are some prerequisites or gaps will be ideally needs to be filled first. The biggest problem or gap at this moment is a methodology limitation. So basically, the release check guide is designed for real data only, and there's no dedicated release check rule for synthetic data. So unfortunately, then you will be forced to apply the release check rule of real data on top of the synthetic data, which is a little bit unfair. So even you can create a very sophisticated model within IDI, and when you're trying to release the realistic synthetic data, then you are forced to remove some minority samples as example. So you're going to destroy the realisticness you're trying to achieve here. In addition to this big methodology limitation, and there are other well-known limitations such as software limitation, you can only run SQL, R, data sets, and the hardware limitation, which is the computational power, and there's no GPU, so there's no deep learning at all in IDI. But if we look positively, yeah, opportunities here, and I think if the awareness, we have reached the awareness of synthetic data application within IDI, I think the stats team is fully aware of this mainstream of research. I think if more people like us to do more research in this direction, and finally we can push this forward. Then, okay, outside IDI, we also trying to evaluate the synthetic data application in health or business, and focusing on the machine learning part. So we're trying to do machine learning predictions, and the data balancing can be an issue, and the data quantity can be an issue. So then here we're trying to evaluate whether we can using synthetic data as a substitute for real data. Basically, we only train machine learning model on synthetic data and test the result on a holdout test data. The second question is, can we use synthetic data for data balancing? As you can see here, if the original distribution is imbalanced, we're trying to use synthetic data to generate specific or the minority class data and put them together, trying to make sure the machine learning prediction is more accurate and fair. And finally, can we use synthetic data for data augmentation in the machine learning prediction model? Basically, we generate synthetic data put together with real data, make the training data bigger, and trying to improve the machine learning efficiency. Based on our result, yes, so synthetic data is super useful in this case. So if you're facing training data limitation, and you want to make it bigger, or you want to make it more representative of the training data set, then synthetic data can be the tool you can use to improve machine learning utility. Summary and the future work. So in conclusion, in a very high level, synthetic data is a powerful tool in data-centric AI, which can help us to generate diverse and enriched data sets. And in social data context, synthetic data can be applied in different scenarios, trying to address data quantity, quality, and the availability issue. And finally, it's not only the high fidelity synthetic data is useful. I think synthetic data at different fidelity levels are all useful for different problems. So you just need to design your data synthesis project based on the downstream task. Okay, if it's only for training, project scoping, or testing, then low fidelity synthetic data will be more than enough. A real example here is we're trying to do collaboration. So we are doing collaboration with Stanford Uni on vaccine evaluation program within New Zealand using T40 Aura data. Of course, we can't give them high fidelity synthetic data. What we do is we generate a low fidelity synthetic data where all those health events are looking real enough, and I'll push that data into GitHub, and they push their code into GitHub. Whenever this data refresh or code refresh, the analysis pipeline will be triggered again and again until we're happy with the result. Then we take the analytics pipeline out of GitHub and apply into the real data and get a result, and which create a very smooth way to do global collaboration in the research space. Okay, let me do a quick demo. So personally, I at work always use R because R is much more popular in the government sector or academic research. But for my machine learning project, I'm a Python coder. I like Python because Python is much more easier than R to do machine learning, and I think deep learning is not possible with R based on my observation at this moment. So I'll just load all the packages, and here's just loads the meter data of the demo real data. Then, okay. So this is a very famous UCI adult income survey data, publicly available. And you can see here there are some continuous variables, categorical variables, and this is a binary classification problem data set. And you got the label, you got two classes over here. So our goal is trying to generate synthetic data on this table. Okay. Then the first step is we can generate the meter data of the real data. And this is a parameter you can change as well. So for example, if we're trying to break down the continuous variables into 4 percentile, then you just put 4 here, and you can see this is the metadata for continuous variables. For categorical variables, basically it will capture the contingency table, which is the count for each categories. Yeah. And then we're trying to generate some low fidelity synthetic data by simulation using meter data only. As you can see here, this algorithm doesn't have access to the real data at all. It only have access to the meter data. Okay. How long does it take to run? I think it should be 2 seconds. Yes, under 2 seconds. Then you got your fake data available. Then if I go here, yep, because by simulation you can see it's ordered by the variable location, and it's all private, but can guarantee you all the categories got captured. To visually check that, let's do a overlapping plot of the synthetic data against real data. As you can see here, the dark blue is the real data, and the light blue is the fake data. From univariate distribution point of view, the simulation model or the simple simulation model is working perfect. And of course, as you can see, here are some outliers. How to fix this? That's very easy. You just need to increase the percentile of your meter data, then it will fix the problem. So now let me change the 4 percentile to be 20. Then as you can see here, go back to age. We used to have 5 percentile number here. Now we got 20. Then based on this new meter data, let's regenerate the synthetic data. And then we do the press B over here, and let's do replot. Then the distribution should align with each other. As you can see here, yeah, it's guaranteed. For categorical variable, it's just perfect because this is simulated based on the counts of categorical variable. So the synthetic data and real data align with each other in a perfect way, and it's guaranteed as well. But if we look at a bivariant relationship, which is a correlation, then you will see we don't capture the correlation at all, which is what we want because this is low fidelity synthetic data. Sorry, this will take a little bit longer to run. Yeah, as you can see here, this is showing the absolute difference of the correlation in real data and fake data. Ideally, we should see all 0, but now, as you can see, there are big variance. So, which guarantee from privacy point of view, there's no privacy issue. And the second group of model we can do in IDI is SMOT. Okay, I'm not going to rerun the whole thing because, oh, I can rerun this maybe. Just take 1 second. Yep. So 39,000 row of synthetic data with 15 variables under 1 second. Yeah, it's quite amazing, the SMOT model. I think it's because of this Google Colab computational power as well. And if we plot for numerical variables, I think the performance is okay. Yeah, the distribution is slightly out, but we probably can do some trick to make it work. But if we look at the categorical variables, there will be big problem. As you can see, they not align with each other very well because SMOT, they treat all the categorical variables in ordinal order. So basically, they will introduce a lot of noise or error in the categorical variables. And from correlation point of view, the correlation is much better than simple simulation model. It's not perfect, but it's good enough. And if you want a quick solution to improve on SMOT, just using SMOT NC algorithm, which is SMOT nominal and categorical. Then as you can see here, the continuous variables doesn't change much, but for categorical variables, it got much better alignment, although it exaggerates the majority classes a little bit. And from correlation point of view, the correlation resemblance is much better using SMOT NC, and this is what we used in the IDEA project. And finally, is deep learning. All of those algorithms are not exciting. I think deep learning is probably more exciting. As you can see here, for this specific generative adversarial neural network model, CityGAN, proposed by MIT back in 2019, still very good. And we do have our own deep learning algorithms, but conscious of time and it's not much value to show the too much technical details about that, which is based on transformer model, and the performance is much better than the MIT model. And the advantage of deep generative model is once the model is trained, basically you can save the length joint distribution into a file like this. Then whenever you load this file up, which is your algorithm or your trained model, you can simulate or you can generate synthetic data as much as you want. And the performance is okay given this algorithm. Yeah, and the correlation got captured in a perfect way. And can we use the trained deep generative model for augmentation? Yes, we can. As you can see here, you can generate as much as you want, and then you can plot it against the real data. And in the real data, it's like 39,000, and in synthetic data, we just plot, we just do 100,000. So you can see here. Then the second question is, oh, can you use that for balancing? Yes, we can. You can generate synthetic data with some condition values for a specific column. Please be aware here is not deterministic conditional generation, which means it will just increase the probability to generate a female over male. It doesn't mean it will generate a female, but we can use a deterministic filter method. You can make sure all your data is coming from female. Then if you want to know more about CityGAN, and here is a proper developed tool called SDV from MIT, and feel free to read through all those guides, which will give you some real examples to do advanced usage of CityGAN. I think that's my presentation today. I'll stop here now. Thank you. Any questions?
There are a couple of questions in the chat already. Jose asks, can this methodology be used for dealing with missing data as a multiple imputation technique?
Yeah, easily. That's right. Yeah, so missing data can be treated as synthetic data. Yeah, I think a lot of algorithm when trying to develop advanced algorithm for synthetic data, they always publish a paper for missing data imputation first, trying to test the novelty, and then they scale it up for synthetic data generation. Yes, so it can be. Elka, is there's NZ planning to release any synthetic data outside IDI for public use? No, unfortunately, I think states they probably working on other priorities. But I don't think that's on their agenda at this moment.
Yeah, they've got the curves, which are modified data, not exactly synthetic. Do you program in the sort of privacy preserving aspects into the model somehow, or um, you run it and because of some parameters you put in, for instance, lack of correlation, you know that it's not going to be an issue from a privacy point of view. Where I guess what I'm getting is, can you set it running and know you're going to get high quality and high privacy preserving data?
Um, Yes and no. Yes, the no part is well-known trade-off between privacy and utility, right?
Mhm.
So this is like a curve. You can only find a balanced point, which is your equilibrium, whatever you call it. And but yes, you can introduce a differential privacy method in your generation process, so it's guaranteed to be uh privacy preserved. But the question is, uh, it really up to the data owner or data custodian's release check rule. For example, in States New Zealand case, right? Even you can do deep learning with differential privacy, which is guaranteed in theory. How can you convince that's the case to the States release check team? That's another challenge, I think.
Okay, thanks. Thomas has a question.
Oh,
Thank you. That was very interesting. I wondered for the first example that you showed us, where you generated the synthetic data in the IDI, and you had problems then getting it output checked. Couldn't you
yeah.
do that outside of the IDI? I mean, you have the dictionaries outside. You can export some summary statistics based
Yeah.
on the existing data and just generate the synthetic data outside the IDI. No?
Yeah, that's right. But that's the low fidelity synthetic data, right? So if you talk about no fidelity synthetic data and low fidelity synthetic data, no problem at all. You can always
Okay.
do that in any environment. Doesn't matter if it's IDEA or not. But if you want to generate high fidelity synthetic data and release it out of IDI, I think it's very challenging at this moment.
Okay.
Alex, thanks for the presentation. When you first, so in the beginning part of your demonstration, you changed the percentile from 4 to 20, and that significantly increased the differences, the discrepancies between the real and the synthetic data. Is it always the case that if you have more percentiles about the real data, the more accurate or the higher the fidelity of the synthetic data will be?
Yes, and it's guaranteed. I can tell you why. So for example, if we have 100 observation, if you remember 100 percentile, you remember all the real data.
Right.
And you look at this bell curve.
Yes.
And if you only remember a mean and maximum, you're going to generate rubbish. But the more segment you remember, the better you, and it's guaranteed. Yeah.
And this is for numeric variables.
Yeah.
What about categorical variables?
Categorical
numerical variables.
Yeah, categorical variables is just guaranteed as well, because you categorical variables is simulated based on the counts, right? That's just a fixed number.
Yes.
And in IDI case, you probably lose some information by doing random up or down three. I cannot remember the name now. Yeah, RR3.
Random rounding. Yeah.
Yeah. But
Random
the
rounding
overall,
to base 3.
Yeah. So the overall categorical distribution should still be perfect. And Stats NZ, they probably don't realize you use this for synthetic data. They'll just give it to you because it's a summary stats.
Yes. What about the correlation between say a categorical variable and a continuous variable, how do you preserve the correlation between two variables?
Okay, in this case, you're talking about high fidelity synthetic data, right?
This is
Uh,
high.
Yeah, because you're trying to capture the table structure, right?
Mm.
Including univariate distribution, bivariant, multivariant. Then that's high
Mhm.
fidelity synthetic data. Then if you talk about IDI case, I think the best chance will be either using Chris-Boss model or you just using Smart NC. It's those two are the best within IDI case. Outside IDI, there's a huge amount of algorithm available. Even some algorithm I personally designed based on transformer model, which is the building block for ChatGPT. That performance is awesome based on our preliminary experimental results, and our paper is currently under review. Hopefully, got published soon. But if anyone want to explore high fidelity synthetic data using deep generative model outside IDI, I'm very happy to help. And inside IDI, I'm happy to give advice, but probably don't have time to help given the limitations we got in IDI. Yeah.
How difficult was it to release your synthetic data using SMART method? Because we did the Chris-Boss method way of releasing data, and it was not that straightforward, but it's manageable.
Okay.
So how manageable is your is yours?
I think if I'm doing it again, it will be very easy because we got reference now, right? You can just reference to. At that time, it's very hard because it's a new methodology and needs to be special approved from VHINs. Yeah, so it takes about 4 to 6 months. Most of the time, it's just waiting or email back and forth. But now I think, 1 month maximum. Question for Luke. Do you have any suggestion for generative synthetic data as hierarchical structure? Household, family, individuals? Yes. So there are two approaches. The first one is you link it first, then you generate. Then the second one is you design some special laws between the linkage of those tables. But that's from deep learning point of view. If you talk about this in IDI, then I would highly recommend you trying to join all the table together into a big table. Then you generate synthetic data on the big table instead of generate those tables individually and link them together later. And you just run the bell. And another advance work here will be, or the lesson I learned before is, you probably want to run a cross entropy check for the table you're trying to generate first to figure out which two variables are deterministic relationship, like 100% positively related. So as example, if you're familiar with Wellington, right? If you talk about Johnsonville as the region, then the city is always Wellington. So for this kind of deterministic relationship, you don't need to generate. You just exclude this relationship in your data generation. And once you generated the Johnsonville, you're using a lookup table to map Johnsonville into Wellington in the city column. So hope that's helpful as well. I'm happy to share more about the future study or future direction. I thought I was running out of time. I think the next three steps about synthetic data application in government sector in New Zealand specific context. There are 3 potential streams. The first one is evaluation framework based on IDI. We need to help states to develop a robust synthetic data release guide. That's one from iteration release check point of view. Second one is population level synthesis, or you can call it digital twin, based on aggregated data. It's not based on uni-record level data. We know, within IDI, you got computational limitation and you can't release it out. Then we can build some model outside IDI with unlimited computational power. The third one is multimodal data synthesis, which is very useful for the health domain. So if somehow we got access to image data along with clinical notes, demographical information from the health database, I think we need to train a multimodal deep generative model. We can generate a health record for one patient in table, image, and clinical notes together in one go. So that's the 3 potential research stream if you want to dive deep in this domain. So that's my final comment.
Thank you very much, Alex.